Broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. This is Rick Kosick, and I think we're going to go ahead and get started. Um, just can you raise your hand right now if you can hear me? I just want to make sure audio is working properly. Good. Okay, sounds like it is. Excellent. Um, okay, so we're going to go ahead and get started. Today, we're going to be talking about modeling contaminant concentrations in ponds and reservoirs using GoldSim. Now, this is going to be an introduction basically to how to do this. It's a obviously a complicated topic, um, and it's really an introduction on how to go about doing this, and then I'll point you in the direction you can go if you want to learn more. Most of what I'm going to discuss are pretty introductory concepts. So those of you who are already well versed in the contaminant transport module, this will be most of what I'll talk about. You're probably already aware of, but I'm going to discuss a few important topics toward the end that you may not be aware of. In any case, it'll be a good overview for even for those who are familiar. I'm going to start because there may be some people who are not familiar at all with the contaminant transport module, which is the part of GoldSim we're going to use to do this type of modeling. So I'm going to start with a really brief introduction to that for those of you who may not be familiar with the contaminant transport module. And then we're going to walk through some examples, and that's really the best way to illustrate this. I'm just going to show you some examples of GoldSim in action. Toward the end, I'm going to address a number of more complex issues that some of you may run into, those of you who have used GoldSim for contaminant transport modeling, how to deal with solubility constraints, for example. And a common problem, particularly with people who are using GoldSim to model mine water management systems, is you may have some ponds that dry out and they actually go completely dry. And so how do we calculate concentrations in ponds that periodically go dry? And although we're going to be talking about ponds and reservoirs and lakes, sometimes we need to discuss how do we model the travel times between those ponds and reservoirs. Oftentimes it's essentially immediate, but sometimes it isn't. So I'll close with a simple example of that. So let me just start by giving you a very quick overview of the contaminant transport module. Again, I apologize to those of you who are already familiar with this. This is for those people who may be attending who the CT module is completely new. So I'm just going to take about 5 minutes or so, 5 or 10 minutes, and just do a very brief overview. So the rest of the talk will be understandable to those who are new to the contaminant transport module. So as you know, the basic GoldSim framework is really a very generic tool. Most of you are using it for, environmental systems, but it's a very abstract, generic tool, the basic framework, kind of like a programming language. But of course, some problems you cannot really solve just using generic tools. So GoldSim has some specialized extension modules, and the one we're going to be talking about today is the contaminant transport module, which is a specialized set of tools that are added to GoldSim to support doing water quality and complex contaminant transport simulations. So what this module does, for those of you who are new to it, it simulates the movement of mass, typically contaminants, through natural and engineered systems. And what it calculates are mass transport rates at defined locations, concentrations in specific environmental media, let's say water in a pond or sediment in a pond. And we can also calculate impacts to define human receptors. So if you're doing a radioactive waste management model, you don't want to stop at the concentration. You need to take the calculations a little bit further and need to calculate impact on human receptors, let's say a dose or a health risk. We're not going to talk about that at all today, but the contaminant transport module does support that. The types of processes that we can simulate are mixing. That's the main thing we're going to talk about today. Solubility constraints, we can do partitioning. We'll talk about that. Advection between ponds or within, let's say an aquifer, dispersion, diffusion, chemical reactions, and we can actually do radioactive decay and ingrowth. We're just going to talk about a subset of these processes today. So the contaminant transport module adds some specialized elements. Again, for those of you who are new to GoldSim, the GoldSim contaminant transport module. And it provides this basic framework for modeling fate and transport. So unlike basic GoldSim, which is completely generic, I mean, it does math, it solves, very, very simple ordinary differential equations. In order to do contaminant transport, we need to solve coupled systems of differential equations. We need to solve essentially the advection dispersion equation in some cases. So there's more physics that are built into GoldSim, into the contaminant transport module than other parts of GoldSim. But it's still quite flexible. So there's very few assumptions that are built into the code. And this is intentional, so you can simulate almost anything. One of the things for those of you, again, who are new to the contaminant transport module, it relies on a feature of the basic GoldSim framework called arrays, basically vectors and matrices. Why does it do this? Because when we're simulating contaminant transport, we're usually simulating multiple species, maybe 5, 10, maybe 50 species. And so the various objects are operating on a vector, on an array of species, not just a single species at a time. So the way we model contaminant transport, we specify some species, we define media, water, sediment, soil, air. We define transport pathways, and that's where mass is transported in stores, and transport pathways are made up of media. And of course, we have to define some source terms. Is there an initial or is there a boundary condition? And again, optionally, we can define impacts. We can basically provide some information to GoldSim so it can convert concentrations to impacts, doses, for example. So of these elements, and you will see these here in a couple minutes, obviously we define species. There's a species element that allows us to do that. GoldSim doesn't understand chemistry. You can define any species you want and name them anything you want. Now, if you're doing radioactive waste management modeling, GoldSim does actually have a built-in database. We won't talk about this today. It's got all of the isotopes that exist in the world, and you can actually pull in all the data for those isotopes, basically their half-lives and their molecular, their atomic weight, and who their daughter products are. But for most, in the mining arena, you're just going to enter, these are the species I want to simulate. And GoldSim knows nothing about them. There's no database in GoldSim that knows the properties of iron. You're going to have to enter those properties, as you'll see. The media are really the building blocks of these transport pathways. And there's two types of media in GoldSim, and we'll see this in our examples. There's fluids and there's solids. The fluid that will be in all your models will be water, of course, but you could have other fluids, air. If you've got some volatile species, you could actually, in some cases, in complicated cases where you're modeling, let's say, some non-aqueous phase organics, you could have a fluid like oil or some organic fluid too. But for most people, you're just going to be dealing with water. But you may have multiple solids. You might have sediments in a pond. You might have soils. You might have different types of rock, different types of aquifer materials, sand, clays. And each one of these has different properties that you're going to have to provide. And those properties are what's going to determine the behavior of the system. They're the key properties. What are partition coefficients between a solid and a fluid? Are there any solubilities for the species within the fluid? So we're going to have to provide that information to GoldSim. So the transport pathways, they're the parts of the system through which mass is transported and stored. And so a transport pathway might be a tank, We're going to be talking about ponds and lakes, but it could be an aquifer, it could be a soil column. We're going to define these properties of the pathways, basically their volume, their geometry. Um, we may have to discretize them, as you'll see. And then we're going to say which media are in the pathways. So if we have a pathway that represents a lake, we might say inside this lake are two media. There's water and there's sediments. And so we're going to have to tell GoldSim what are the media that exist inside this pathway. So the way you should think about pathways is we're going to put mass. Mass is going to enter a pathway, usually at a particular rate, or we might have an initial condition. It's going to move through the pathway and it's going to leave the pathway. And it leaves the pathway, it's maybe dispersed or decayed, and it will or delayed. And so the transfer pathway is like a transfer function. It takes mass in and it spits mass out. There's a number of different types of transport pathways. You can hook them together. So we're going to hook these transport pathways together by telling GoldSim how mass moves from one transport pathway to the other. In the examples we're going to look at, we're just going to have advection. We're going to have a pond that has water move, let's say, from one location, one pond, to perhaps another pond. But you could have other types of mass fluxes. You could have diffusion. You could diffuse from one location to another location. You could diffuse out of sediments into a water column, for example. There's multiple types of transport pathways. We're going to focus on what we call a cell, because a cell is what we would use to model a pond or a reservoir in GoldSim. We'll do I'll show you one brief example at the end that has another type of pathway called an aquifer, and I'll show you what you can use that for. But almost all of our examples, we're going to just focus on this thing called a cell pathway. And so what are cell pathways mathematically? A cell pathway is a mixing cell. It's basically, I mean, if you look at the image, it's got a little mixer in there. It's a well-mixed volume. That's the way you should think of a cell pathway. All right, we can have multiple media in the cell pathway, water and sediment, let's say. Really key point here that people often forget and they need to understand, even those people who have used GoldSim quite a bit, and I'll show you some examples of this. When mass enters a cell, it's instantaneously mixed throughout the cell. Doesn't make any difference how big the cell is. It's instantaneously mixed throughout the cell. So if you have a cell representing Lake Superior or Lake Michigan, right, or the Atlantic Ocean, right? Basically, when mass enters that cell, it's instantaneously everywhere within that water body. So you need to keep that in mind. A cell pathway is instantly mixed and it's instantly equilibrated. So if we have water and sediment in a cell, and there's a partition coefficient for a species between the water and the sediment, as soon as mass enters that cell, it's instantaneously equilibrated through all the media. Just something, we're going to discuss this a bit further, but I want you to keep that in mind. A cell pathway is instantly mixed and equilibrated. We can do some things like add solubility constraints to a cell. We'll see an example. Of course, the cells have to be able to have mass enter it, so we can specify an initial condition or we can specify a boundary condition for the cell. Mathematically, what we're doing is when we have cells hooked together, it's mathematically equivalent to a network of finite difference nodes. And so that network of cells is being solved as a system of equations. That's essentially what's happening behind the scenes in GoldSim. Another thing that's important to point out, GoldSim, these cells that we're going to use in all pathways, they conserve mass. All right. So we're going to move mass through the system, and we're certainly going to conserve that mass, obviously, unless it decays, and we specify a decay rate. But it's simulating the movement of mass. It's the contaminant transport module itself is not simulating the movement of water. You're simulating the movement of water in a separate part of your model. That's probably using pools and reservoirs, and you're tracking the movement of water through the system, right? So the water part of your system, the movement of the water, serves as an input to the contaminant transport module. right? And I'll show you what I mean by that in a minute. Okay, so that's just the background now. And now we're just going to spend the rest of the webinar, we're just going to talk through some example models. And they're going to start very, very simple, right? And we're going to add a little bit more complexity as we go. So the very first model we're going to look at is extremely trivial. All we're going to do is we're going to mix two inflows. So imagine we have a pond and we're pumping 100 cubic meters per day of water out of the pond, and we're pumping in 100 cubic meters per day of water into the pond, but we're doing that in two different streams, right? And in one stream, we're putting in 40 cubic meters per day, and it's got two contaminants, X and Y, and they have certain concentrations. And then we're pumping in 60 cubic meters per day, same X and Y, but they have different concentrations. So that's all we're doing here. Very, very simple. All GoldSim is doing here is mixing them together. You could actually do this simple model in GoldSim yourself. You could build a GoldSim model without the contaminant transfer model and do this calculation. But it would quickly get very awkward if you had lots and lots of ponds and lots of species. GoldSim just does it for you, and you'll see how that is. Now, in this particular model, the initial concentration is 0. So the pond starts with nothing in it. So we'll look at that model. That model just looks like this. And there's our mixing cell right here representing the pond. And we have a volume in the pond. As I said, it was 100 cubic meters. And we have this mass input rate. Well, the mass input rate is actually coming from those two. We have an inflow and a concentration, and an inflow and the concentration. And what you're going to notice here is this is a vector. Why is it a vector? Because these concentrations are vectors of species. So there's two species. So C2 is an array with two items, 2 grams per cubic meter and 4 grams per cubic meter. And therefore, this expression is also a vector of species. So if we go ahead and run this model, we're just mixing these two inflow streams. You see that we get a result that looks like this, quite simple. We started empty, and then we reached a steady state. At some point, the concentration in this pond reaches a steady state. And in fact, we could have predicted what the steady state values were, because the steady state values would simply be the mass input rate divided by the flow rate, right? That's what the ultimate steady state value is. And here you can see it took, I don't know, 5 days or so in this particular case to reach steady state. So there's our simple, a very, very simple concentration example. We're just mixing two streams. So now let's just talk. We're going to take a second to say, what did GoldSim actually do here? Well, we provided a flow rate in that mixing cell. Right, we actually have an outflow. There's my flow rate. We provided a flow rate. We also provided the concentrations, right? And we had an input rate. Well, we didn't provide we provided an input rate. Well, that input rate was a constant rate. It was the mixture of those two. Those two rates. GoldSim just solves this differential equation. That's all it's doing here in this very, very simple case. We're solving for the amount of mass, and the concentration is just mass divided by volume. In this model, the flow rate Q and the volume were constant, right? We had a constant flow rate of 100 and the volume was 100 cubic meters, but they don't have to be. And we'll see that in a minute. Let's make this problem just a little bit more complicated. It's the exact same problem, but now I provided an initial concentration for X and Y. So in the previous model, X and Y started at 0. Now we're going to have X and Y. They start with a different an initial concentration. So if we look at that model, the structure is the same. It's a little bit more complicated in that the way you put in boundary conditions to a cell, to any pathway, is you can put in an initial mass, You can put an input rate, is what we did before. But in this case, we want to say I have an input rate and an initial mass, right? An initial mass and an input rate. And the way you do that is you actually use an integrator to do that. And you say, I'm going to integrate my initial mass. That's my initial mass, initial concentration times initial volume. Then I have that mass input rate, which was the same mass input rate we calculated before. It was that equation. And that represents the cumulative amount of mass that you've put into the cell. And then the pond pathway just has an option, say, what's my cumulative input? And there it is. So that's the method, if you've never done this before, of how do you specify both an initial concentration and an input rate, a boundary condition into the pond. So if I run this model, we're going to reach the same steady state, right? We're just going to reach it from different directions now, right? So this guy started at 10 instead of 0. This guy started at 3, but we ended up reaching the same steady states, right? So boom, GoldSim did the mixing, brought us to steady state. All right, again, very simple model. But now let's think about what really happened there, right? So, and people often don't think through this when they're defining their ponds or the mixing cells that represent the ponds. This model, it took a certain amount of time to reach steady state, right? Well, how did that work? Why did it take a certain amount of time to reach steady state? Well, concentrations in a pond have inertia, right? And how quickly they respond to changes in what's coming into the pond, it's a function of how long it takes the pond to turn over. Basically, it's a function of the volume divided by the flow rate, right? If I had a very, very, very large volume, I've got a lot of inertia in that pond, it's going to respond much more slowly. And so that's how we should think about how these guys operate. So let's examine the behavior of this system as a function of the pond volume. So what I'm going to do is I'm going to use the scenario module in GoldSim, and I'm going to run the model with different volumes, right? All the other inputs are the same, right? I'm going to between these examples, except the initial volume is going to vary between 10 and 1,000, right? I'm also going to make one little change. I'm going to in the last case, the incoming concentrations were constant. I'm going to cut them in half at 50 days. I'm going to have a concentration for both of those input streams, and then 50 days in, I'm going to cut those concentrations in half, just to make the model a little bit more interesting. All right. So now, if we look at this model, all right, and we open it. The first thing I'm going to point out to you is I set this model up with scenarios, right? So I created 4 different scenarios, and what the scenarios are defined as is just the initial volume. It's a 10, 100, 500, or 1,000. So we can, the idea here is to see how the results change with different volumes, right? The flow rates are the same. The volumes are different. How much water this pond has. And so if I run these 4 scenarios, let's go ahead and compare them. And let's just plot, let's say, the concentration of X. And so here what you see is the red curve is when we had a very small volume, 10, and the pink curve is when we had a large volume, 1,000. Right? So this is what you would expect. If you have a very, very small volume, it doesn't have any inertia. It reacts very quickly. It started at 10 and very quickly it went to steady state. Whereas with the large pond, it took a long time to get to steady state. And then at 50 days, we changed the inflow and then it had to readjust to a new steady state, right? And obviously you'd see the same type of result for the other species. The smaller the volume, the more quickly the system reacts. So in the previous examples, we treated that cell as having a constant volume, right? But in the real world, in all the models you're going to build, unless you're simulating, I don't know, a tank, right, where you're keeping the tank at a constant volume. In the real world, that's not going to be the case. Your volumes are going to change all the time during your simulation. So in order to model changing cell volumes, we need to use a reservoir or a pool that track the volume. That's your water balance model. And then you're going to link that to the cell as an input, right? So in this case, we're going to look at the same model, very similar to what I just showed you, but I'm just going to have one species now. And what I'm going to do is I'm going to have two inflows coming in, but they're not always equal to 100. So I have an outflow from this cell, which is exactly 100 cubic meters per day. So let's say I'm pumping at 100 cubic meters per day. But my inflows are noisy. I put in a noisy signal, so they're about 40 cubic meters per day, plus or minus. And this one is about 60 cubic meters a day, plus or minus. Well, since these guys are variable and this guy is constant, that means the volume of water in the pond is changing with time, okay? I'm going to do one more thing to make this model a little bit more interesting is I'm going to run it in scenario mode again, in which I have three volumes. The pond volume is, its initial volume is 100, 500, and 1,000, right? And let's see how it performs. We're going to just add one species just to make it a little bit simpler, and the pond starts empty. So if I open up this model, let's just look at how I simulated it. The very first thing I had to do is, you'll notice now I have a pool element in here. I didn't have a pool element before because I didn't have to track the volume. I didn't have to track the volume because I said it was constant. So I just put a number into the mixing cell. The mixing cell needs a volume, and I just had a constant because I didn't have to model it. In this case, we're going to keep track of what the pond volume is. And the pond volume has these two inflows, and those inflows are noisy. And just to show you how I simulated them, I just simulated them using a stochastic element that gets resampled every day. So that's all I'm doing. So for example, this guy was 40 plus or minus 4 cubic meters per day. I'm going to resample it every day, and I'm also going to auto-correlate it so it's not bouncing too wildly from day to day. So that's all I did. I had a random inflow, but I have to keep track of the pond volume. And that pool element then becomes the input here to how much water is actually in the pond. We'll go ahead and run those three scenarios now. And again, with 100, 500, and 1,000 as the initial volume, right? Let's first look at, just so you can see what I was simulating. Those were the inflows. So the inflows are noisy. Those are my two inflows. And that results in pond volumes that look like this. So remember, I had three scenarios. So this pond volume is bouncing around 100, this pond volume is bouncing around 500, and this pond volume is bouncing around 1,000, but it's not a constant pond volume anymore. Now let's look at the concentration in those ponds. And now we're going to see what we really saw a little bit in the previous example. How quickly does the system respond to changes, right? We're putting a constant concentration, but we're putting a different flow rate. So the amount of mass we're adding at every day is different. And so you see when we have a smaller volume, in this case, 1,000 cubic meters or 100 cubic meters as my initial volume, it's pretty noisy, right? That's the concentration of the pond. That pond is reacting to this new mass that's coming in pretty rapidly, right? Because we've got a pretty small volume. As the initial volume gets larger, you see that all those changes kind of get ironed out, right? And so you see when we have an initial volume of 1,000, you don't see this guy react even once he's at steady state. He reacts quite slowly. In fact, let's just zoom in around, when we're at steady state. So when we're at steady state, we still have changes in our inflows, um, but we're not really at steady state. We're at pseudo steady state because it's bouncing around. But you can see how slowly the large volume pond reacts as opposed to the small volume pond. This is exactly what you would expect, right? I mean, we've got a lot of inertia if we've got 1,000 cubic meters compared to 100 cubic meters, right? So this is really an important point because oftentimes people lose sight of the fact that the size of your pond um, how you represent your lake or your pond or your reservoir in GoldSim and how you discretize it can make a big difference. So I want to show you a little example of that. You know, again, we smoothed out the variations when we had this large. And the reason we did that, keep in mind that we're instantaneously mixing the mass through the entire volume. So the larger the volume, right, the more we're smoothing out that mass. But in the real world, this may not be realistic, right? If you had a very small pond or a reservoir, it may be realistic that the whole thing becomes well mixed. But in other cases, it may not be the realistic at all. And let me just show you a little example of that. Imagine that you had a kind of a large, deep pond in which we're just adding some mass here at the top. And then it's pumped or it overflows, let's say, into this downstream pond, right? Well, the question you have to ask is when that mass comes in, does it actually mix through the entire pond? Let's say it's very, very deep, and let's say it's we're in the summer and we've got some temperature differences. The deep water is cold and the shallow water is warmer, and so there's a thermocline here, and maybe there's not a lot of mixing. And how would we represent a system like this in GoldSim? Well, let me show you an example that kind of simulates that system. Um, this model basically um, is I basically built um, three representations of this system. All right. In one way, I represented the first pond as just one well-mixed cell. There it is. Mass comes in, and then it goes to the next day, and then it leaves the system. That's the one representation. And the second representation is I've represented this pond using two mixing cells, an upper layer and a lower layer, right? Um, and what I've done here is I've created it flows into pond two, but I also have water flowing down to this lower layer. And if I were to look at the lower layer, he is flowing up at the exactly same mixing rate, right? So the rate of mixing downward is the rate of mixing upward, all right? So we're mixing, and you can imagine is that mixing rate determines everything. If the mixing rate is very, very high, it's equivalent to having just one well mixed cell, right? If the mixing rate is very, very low, we're going to have a very different answer. So what I've done here is I'm plotting the concentration in the second pond. I want to look at the concentration here in the second pond for three different cases. One in which I assume the entire pond is just well mixed. One in which I have a mixing rate and it's a high mixing rate, and one in which I have a mixing rate and it's a lower mixing rate. All right, and so if we run this model and look at the results, um, we see something like this. So if I just have one cell, that's the red curve, you'll notice it's very similar to the green curve in which I said, oh, it's just two cells with a very high mixing rate. Basically, the concentration in the downstream pond looks about the same, right? But if I have a very low mixing rate, right? Which means I enter into this top part of the pond, and not much of the mass that enters the top part of the pond moves to the bottom part. Some of it does, but not much. And so what happens is the concentration downstream is significantly higher than if we were to assume the entire mixing cell, the entire lake was well mixed. Do you see what's happening there? So this is why this assumption that you have to be careful when you make assumptions about a pond or reservoir being well mixed, because the downstream concentrations can be wildly affected by that assumption, right? If everything just sticks near the surface, right? If I had no mixing at all, right, we would have even a higher concentration here, right? So it's something you need to keep in mind when you're simulating ponds and reservoirs. How well mixed are they, right? Now, unfortunately, as you can imagine, coming up with these mixing rates is it's not something that's easy to measure. You would typically just have to calibrate or make some measurements in the pond or reservoir, and then try to calibrate your model to see if you can match those differences. So just to let you know what we solved there, so you can get an idea of what GoldSim is doing. Remember, I had 3 mixing cells in this model, right? 1U, 1L, and 2, right? And so what GoldSim did when we built those models, I didn't have to write these equations. GoldSim wrote these equations. It says, well, what's the governing equation for the upper level of the first lake? It's what's going out is the mixing rate downward, all right? Plus the mixing, what's coming in is the mixing rate upward. We're also, another thing that's going out is the flow to the downstream, right? And then we have some input that's coming in. So that's the differential equation that GoldSim wrote for that layer. The bottom layer had a simpler differential equation, and third lake had this differential equation. So we had 3 differential equations that GoldSim had to solve, and that's what it did. It's formed those differential equations, and it solved those implicitly as a system of equations. So that's mathematically what it's doing in the background. But the equations aren't rocket science, right? You can easily write what that governing equation is for each one of those mixing cells. Okay, the next thing I want to talk about is partitioning, right? So GoldSim can, and this is important because partitioning can make a huge impact on your concentrations. So GoldSim can simulate equilibrium partitioning of species between water and solids. We can do, if you need to do non-equilibrium partitioning, you could do that too. It's way more complicated. We won't talk about that. But equilibrium partitioning just means we have a partition coefficient, and if we have water in some solid in a cell, instantaneously, that partition coefficient determines the ratio of concentrations, and it's going to happen instantaneously. You're going to see that solids can be assumed to be stationary or suspended in the water. So we'll talk about why that can make a huge difference. But the key point here is partitioning onto a solid phase can have a huge impact on transport in your systems. And so if it's possible, we don't want to ignore it. So let's look at a simple example where we have this pond again, and we just say the pond has a constant volume, all right? It's got 100 cubic meters per day flowing through it, all right? There's no mass coming into the pond, but we have an initial concentration, we have an initial amount of mass in the pond at the start of the simulation, right? So we have 2 species, X and Y. We have 1,000 grams of mass in this pond. But we don't just have water in the pond, we also have sediment in the pond. And we're going to assign partition coefficients for Y. So Y partitions between the water and the sand, or the water and the sediment. X does not partition onto the sediment. It's all in the water, okay? So let's take a look at that model. And so in this model, I had to create two, I had my water, but I also have this sediment, right? And the sediment had, it requires some partition coefficients, right? This is basically what is the ratio, what is the ratio of the concentration in the solid to the concentration in the water, and that, by the way, they have units of volume per mass. And you can see I have no partitioning for X. There is no concentration in the solid for X, but it does partition, Y does partition. Right, so that's how I set my model up. And if we look at my pond, I've said I've got an initial volume water and initial mass of sediment, and they're constant. And I have an initial mass of each species that just starts inside the cell. So if we run this model, let's first look at the mass in the pond. And what we see happening here is, remember, the pond is 100 cubic meters per day of water flushing through it. You'll notice that X flushed out very quickly. By 5 or 6 days, all of the mass had left, whereas Y took much longer to flush out of the system. Well, that's because Y was partitioned onto the sediment, whereas X was not partitioned onto the sediment. And we can see that if we look at the concentration in the pond itself. This is the concentration of water in the pond. And you can see that the concentration in water for Y is not 10 like it is for X. It's a smaller number because some of the mass is partitioned onto the solid. And therefore, remember that what's leaving is Q times C, Q times concentration, and the concentration is higher for X, so therefore it flushes quicker. So very, very simple model. Now you have to ask the question again, is this a realistic assumption that all of that water is in equilibrium with all of the sediments? It may not be, right? I've modeled systems in which I would say, well, what I'm going to do is I might model this system having two layers of two cells represent the water. I have the main water body, and then another cell that represents the water that's in contact with the sediments, right? You assume that small amount of water that's in contact with the sediments is, we're partitioning into that. And then this cell over here has no sediments into it, but we mix between the small volume of water and the main body of water, right? That's what would really happen in most situations, unless you had a very turbulent pond or lake, that there's some internal mixing that is required in order for this mass that's sitting here in the sediments to actually reach the main water column. So that's something to think about. But let's look at a model that, oh, by the way, in that model, here's our differential equation. It's the same differential equation. The difference is we're going to calculate concentration in a different way. The concentration is not just M over V, but it turns out it's going to be M over V plus mass of sediment times the partition coefficient. And so that's where we're coming up with the concentration. But now let's look like a slightly different model. And this one is it's exactly the same as what I just showed you. The difference is I'm going to assume all of the sediment is suspended, okay? It's not just sitting at the bottom of the pond, it's suspended in the water. Now the assumption that we're at equilibrium between the water and the sediment becomes much more realistic, of course, right? But that's all we're going to do, right? And in order to do that, my model, it looks like this. And the only difference I had to do here is I had to click this box. And this box says this solid is suspended in the fluid directly above it, right? So this solid is completely suspended in the fluid above it. All right, so that's all I've done here. By the way, if you had a situation where some of the sediment was suspended and some wouldn't, you'd have to add two solids here, one with the box checked and one with the box cleared. Here we're saying all of the sediment is suspended, right? And so now if we run this model and we look at the mass in the pond, it's identical for those two species. And the reason it's identical is because it doesn't make any difference that Y is partitioned onto the sediment. The sediment is moving with the water. It's flushing right out, right? So the amount of mass in the pond is the same, and we can see what the concentration in the water is, right? This is the effective concentration. So GoldSim will actually calculate, in this case, if we look at the outputs, it actually calculates two concentrations in water. It says, what is the concentration in water and what is the dissolved concentration in water? The concentration in water is the effective concentration in water. This means this is the concentration including the suspended solids. I can also just look at the dissolved concentration in water, and now we see that there's a difference, right? But we don't really care about the dissolved concentration because it's all of the sediments are moving, the suspended sediments are moving with the water, right? And so this concentration would be what you would see, let's say, if you took a sample and you put it through a filter, right? Whereas this is the concentration you'd see if you just sampled it and analyzed it with the sediments. This is important, right? Because if you really do have, there's many species that, metals that might be strongly sorbed onto solids, but if they're suspended, they're moving with the water, right? And you're moving all of that that metal with the water. So it's just something that keep in mind here. We can represent this process in GoldSim. The next thing I want to talk about is modeling solubility constraints. And many species have solubility constraints, right? And the question is, how do we represent those? Now, in a complicated system, we really have to, we may have to use a geochemical equilibrium code to do this, right? Because there's a lot of complex chemistry going on. But in some cases, we can use a simpler approach, and that's what I'm going to do here. I'm just going to say we can tell GoldSim to simply specify a solubility limit for a species. So basically, we're going to tell GoldSim this species can only hold so much mass of this, or the concentration is limited. We can just tell that to GoldSim, and GoldSim will enforce that. So we're going to do a little simple model in which we have X and Y they're released into a pond at a particular rate of a certain mass per day. We're putting this in. We have water flowing through the pond at a constant rate. Y does not have a solubility limit, but X does. X has a solubility limit, so the concentration is limited. So if we run this model, the system I have set up here, if we go into look at our species element, again, we have these two species, X and Y, but now if we go and look at the water, the fluid, you'll see I have a solubility specified here, all right? Well, let's go look at that solubility and let's look at how I actually defined it. And you'll see that the solubility, there's my two solubilities. X has a solubility, and Y has a negative solubility. And you might say, what does that mean? Well, GoldSim interprets a negative solubility as infinite solubility. And nothing, has infinite solubility, but the solubility may be enormous. So if I would get the same result if I would have put 10 to the 10 in here, right? The reason I put a negative number is the way GoldSim works internally. In a small model, you would never notice this. In a very, very large model, the model's going to run faster if you put in a negative number for things that don't have solubilities. And the reason is when GoldSim sees a negative number, it can skip a whole bunch of calculations internally. Whereas if it sees 10 to the 10, it still has to go through those calculations to see, oh, have we hit the solubility limit? So just a little hint there, if you want to have a species that has no solubility limit, you just assign it a negative number. So if we go ahead and run this model, remember, we said that X has a solubility limit. Let's look at the mass leaving the pond. And what you're going to see here is X leaves the pond at a slower rate, right? Y leaves the pond quicker, and X leaves it slowly. By the way, what we did here just is X and Y entered at a rate of 10 grams per day for the first 40 days, and then we turned it off. That's why you see this behavior. So what's happening here? Well, let's go look at the concentration of those two. And you see what happens here is we hit the solubility limit. There it is. We're at the solubility limit of 15 grams. So remember, the flux out is Q times C, right? Well, since the C here is being held at a lower value, the mass transfer rate out of the cell is going to be lower. In fact, it's basically proportional to the concentration, Q times C, right? So our mass transfer rate is lower, and therefore the mass is going to flush out of the system at a slower rate. When we have a solubility limit, by the way, we can calculate the precipitated mass, how much mass is not in solution because it's above the solubility limit, and that's what I'm plotting here. And again, it's always 0 for Y, but here we're adding mass and it's precipitating out of solution up, and then we stopped adding mass and it slowly started dissolving. And then, by 90 some days, everything is back in solution. We don't have any precipitated mass left. All right, so we're keeping track of how much mass is precipitated out of solution. It's just sitting at the bottom of the cell. It's not moving with the water. That's the key point. It's not moving with the water. Okay, here's a problem that for those of you who have done a lot of GoldSim modeling, you can run into this problem in GoldSim, and it's a real problem. It happens in the real world. In some systems, if you have a small pond at a mine, the pond can actually go dry for some periods, right? It may, due to evaporation, and the pond evaporates and then it fills back up with water, and then it drains again and it fills back up with water. And you may be interested in tracking the concentrations in this pond, but the pond keeps on going dry. Well, as you can imagine, if you think about it, if you remember the equations I showed you, concentrations are calculated as M over V, right? Well, bad things happen numerically to GoldSim when the volume goes to 0. It's not going to be happy with that, and we're going to run into some numerical problems. So I'm going to show you the method for how to solve that, and it's important that you're aware of it. This method is discussed in great detail in the help system and the user's guide in the appendix. I'm just going to go through it really quickly, but if you want to know more the details of why this works and what's going on here, the help system will show you this. I will just give you a warning here, though, that if this is really happening in your system, if you've got a pond that has a whole bunch of metals in it and it's going dry, right, due to evaporation, you've got some ugly geochemistry that's probably going to go on there, right? The pond is going to be some pretty gorgeous colors, right? You're going to have a whole bunch of stuff precipitating out of solution, and it's likely that you're not modeling that process, right? So just keep that in mind, that in the real world, when ponds go dry, the chemistry at very high concentrations when you're evaporating water is going to get pretty complex. But let's ignore that for now. We just say we want to model a system and not worry about that complex geochemistry that where my ponds occasionally go dry. So to do that, I'm just going to build this little model. It's a single pond again. It's got water coming in at a constant rate, at a constant concentration. But I'm going to vary how much water goes out, right? So it leaves at the same rate it comes in initially, and then it leaves at a higher rate, and then it leaves at a lower rate. And the reason I'm doing this is I'm going to, this pond is going to go dry and then fill back up, all right? And let's just see what happens when we do that. Let me just check something to make sure I've got this properly set. Okay, good. So if we go ahead and run this model, we're going to get 2 warning messages. And here's something I want to tell everybody who uses GoldSim. When GoldSim gives you a warning message, don't press no here, okay? Go read the message, because there's going to be important things going on here. In fact, if we go and read this message, GoldSim is very unhappy right now. It says, hey, your fluid volume is changing very, very rapidly. This may lead to inaccurate concentrations. And then there's another message. Hey, we have no water in the cell at all. This is going to create problems, right? And then it points you, it says, to minimize these errors, go do this, points you to a part of the user manual, which I'm going to do right now. But the concentrations we're going to produce here are wrong. We're warning you that they're probably going to be wrong. So read these messages. If we let's first look at the pond volume to see why we ran into this problem. So that's what the pond volume did. We were constant, then we went dry, and then we basically filled the pond back up. Okay, my concentrations look like this. All right. So let's just look at the concentration first. So we reached a steady state of 100. Remember that was what was coming into the pond. And then the pond went dry, and our concentration jumped to an enormous number. And then it went to 0, and then the pond started to fill up again, and my concentration jumped to an enormous number and then recovered. These spikes right here are wrong. This all should be 100, right? We're at 100. We could say we're at 0 when the pond is dry, but we're at 100. Then we go to 0. Then we're at 100, and we're at 100 again. So this is nonsense right here. These are crazy, inaccurate numbers because GoldSim did not like the fact that your pond went dry and then started to fill up again. That's why we got 2 warning messages. The first warning message was for this guy. The second warning message was for this guy. We told you, you got problems. How do we fix it? The documentation talks about a number of ways to fix it. I'm going to show you the easiest way that's appropriate for mine water balance and mining models. We're going to do 2 things and 2 things only, okay? The very first thing we're going to do is we're going to say, I'm not going to allow the pond to go completely to 0. I'm going to say that the pond always has a little bit of water in it. Let's say 0.01 cubic meters. It's a tiny number, right? And it actually probably does have a little bit of water in it. We're just going to put any very, very small number in there. That's the first thing we have to do. And the second thing we have to do is we have to change a setting on how GoldSim does a calculation. And we're going to come up here to Model Options, Contaminant Transport, and you'll see this solution precision. It defaults to medium. We're going to set it to low. And you might say, oh, does that mean we're not going to do accurate calculations? No, it's fine, all right? The solution precision is primarily helpful for when you are doing radioactive decay and ingrowth, and when we have complex solubility systems where we're hitting the solubility limit a lot. Under those circumstances, higher precision allows GoldSim to solve the equations more efficiently, but it has a downside in that those little tricks we use when we use medium or high precision, they break down when cells go empty. They weren't designed to have cells that are empty. The low precision says, I'm okay with the cell being empty. Okay. I'm not going to do a great job if you have radioactive decay and ingrowth, in which case there's another method for approaching this that's written in the manual. But for most people, we don't care about that. All we want to do is I want my cell to go empty. I set my solution precision to low. I set my volume to a very small, my low volume to a very small number. And now when I run the model, you'll see that I get reasonable results. My concentration doesn't go to 0, it's still at 100 because I still have a little bit of water there. But that's okay. That tiny little bit of water has a concentration um, uh, uh, it, well, this is that tiny bit of water has a concentration of 100 milligrams per liter. Right? So we are now handling this properly. And again, the trick was make sure you have a tiny amount of your lower bound is not 0, make it a very, very small number, and set the solution precision to 0 or to low. If you want to understand why this works, the documentation discusses it in great detail for those of you who are interested. The final thing I want to discuss, and then we'll wrap up, is in many cases, you're at a mine site, you're looking at movement of water between ponds and reservoirs, and the travel time is going to be instantaneous, right? But in some cases, there may be a significant travel time between one location and the next. For example, if a pond leaks into an aquifer and then that discharges downstream to a pond or a stream. In these cases, we can use an aquifer element to represent this system. I don't have time to talk in detail about aquifer elements, but I'll just show you a model that represents this. Here's a model where we have a pond. It leaks through some sediments that then go through an unsaturated zone, that then go through an aquifer, that then go to a stream, okay? And the way we're modeling this particular system is we're going to use a couple aquifer elements to represent this system. And the model looks like this. And if we go in and see how we simulated it, we have our pond, which is a mixing cell. We have an aquifer element, which represents the transport through the sediments, because takes a while to move vertically through the sediments. Then it takes a while to move vertically through the unsaturated zone. Then it takes a while to move horizontally through the saturated zone. And then we have a stream, which is another mixing cell, okay? Could be another pond. We could have maybe discharged into another pond. These aquifer elements, they have properties like how long are they and what's their area and what's their dispersivity and what are they full of. They basically solve the one-dimensional advection dispersion equation, right? That's what they're doing. So there's going to be delay from this concentration showing up down in the stream. There's also going to be dilution in this particular case. So if I go ahead and run this model and I look at my results, they look something like this. If we look at the concentrations, we see, there's the pond concentration, there's the concentration leaving the sediment, there's the concentration leaving the saturated zone, unsaturated zone, there's the concentration leaving the unsaturated zone, and then downstream, or eventually in a stream, we'll plot the log concentrations so you can see it a little bit better. And so you see what's happening at each step of the way. We're having a delay, which is what I wanted to point out. We're also having dilution here because the flow rate through each one of those things is increasing, right? So we're not just getting a delay, but we're getting a dilution. The bounciness here is because my stream is a variable flow rate. But that's an example of how we can actually delay the transport from one cell, in this case the pond, to another cell, in this case the stream. And we're capturing that delay in this way. It's not an instantaneous thing. Okay, so we went through a lot fairly quickly. I just want to wrap up. We can model ponds and reservoirs just using cell pathways. in most cases, you're going to need to couple your pathways to a reservoir pool element because your cells, your ponds, your reservoirs don't have constant volumes. In some cases, you may just do on a simple mixing, but in other cases, you're going to want to represent things like partitioning and solubility constraints. GoldSim can do that. You can create very extremely complex multidimensional models just using combinations of cells and aquifer pathways. If we just hook these two, you saw the simple example I showed you there, but you could get a very high dimension model by just hooking together these zero-dimensional cell is basically zero-dimensional, and a path and an aquifer, which is a one-dimensional component. For those of you who want to learn more, the very first thing I can tell you is take the online course. A couple of the examples I showed you here are directly from the online course. This online course has about 60 examples. It talks about everything here in much, much, much more detail. Probably will take you 3 days to take the course, but it's very detailed, 60 examples. You'll learn all about everything we just talked about. We have our model library that I really encourage people to visit. It's got some water quality and contaminant transport models that you can take a look at. And of course, as always, if you've got questions on how to simulate a particular process, we really do encourage you to send us questions. Don't hesitate to do that. Go to our help center, and you can always submit a request there. All right, I've gone over. I apologize for going over, but thanks a lot. I will post all of these examples and a recording of this webinar probably either late tomorrow or by Monday. All right, thanks a lot for your time, and have a good day.